Okay, we're in section 137 now. We're getting very close to the end. Contents to look over, examples to do, and exercises to start thinking about. This is my version. My name is Ron Bannon, a draft version of my adaptation of Webster Wells' Advanced Course in Algebra that's date back to 1904. The PDF document that you're looking at now was being made available to the Prison Mathematics Project participants only. At some point in the future, it will be published. If you're interested, a student or teacher is interested in this material, just email me and I'll let you know when it's going to get published and how to obtain it is. Yeah. My email address is Bannon. That's B as in boy, the @ symbol, NNON.US. All right, tough section. It's about biquadratics. I'm going to say, you read through it. It's a tough read, but you read through it, try to make some sense out of it. To put this thing in a historical perspective, it's really no longer taught. All right, is it an important technique? Well, it's hard for me to say if it's important or not. I'm sure that people who code computer algebra systems are well aware of all these tricks that are being done. All right. One of the complaints with Wells, though, is that some of this stuff might be really tricky. All right. So I'm going to say I give you the overview of what he talked about. This is an overview, and I try to write an overview down. All right. Now, again, I'm looking at it, and I'm saying it's really a long-winded. But if you machine, it's not long-winded. Machines can go through these really long-winded things quite quickly, but humans can't. All right. So humans need a simpler way of doing it. So I want to point out if I were confronted with this. Now I want to point out this was solved. If you read through that section, it was solved using Euler's technique. All right. However, if I were doing this, I don't think I'd resort to Euler's technique to do it. All right. So I'm going to read this, and it says over here, okay, I do not think I would use Euler's method for solving a biquadratic. But that's really not the point I want to make here. In general, it is a good idea to study methods that may at first appear to be quite convoluted. However, I do want to emphasize that we're trying to look over some historical methods that will hopefully improve your ability to consider alternatives. It's good to have alternatives, because I'm always saying that, if things are not working out the way I want them to, I want to have an alternative. I want something else to try. All right, but what's my the thing I like to do? I really do like the rational root theorem. Not that it works. I'm just saying if it does work, it works nicely. Right? Does it always work? Absolutely not. So I'm going to just look at the candidate roots of it. And I want to point out it's really kind of simple to do that. The candidate roots would be the factors of 21, which would be 1, not 2, 3, not 4, not 5, not 6, but 7, not 8, not 9, 10, 11, 12, up to 21. The factors of the coefficient of x4 and 1, so it's going to be plus or minus this. So how many are there to consider? There's no guarantee it's going to work. There's going to be 8. Now, which ones would I try? I don't know. I guess I could try 1, right? Let me put this down. So I'm going to say f of x. That equals, let's see, x4 minus 46 x squared minus 24x plus 21. And I think this is quick. What do you get? 1 minus 46 minus 24 plus 21. That doesn't look promising, does it? That's not 0. I'm going to erase it. That's no good. So I'm going to try now. Again, like you say, it's very thuggish. I'm trying. I'm going to try f of minus 1. What do you get there? 1 minus 46 plus 24 plus 21. Well, it looks like that works pretty good. So 24 and 21 is 45. 45 plus 1 is 46. This does equal 0. So now I know there's a factor. Let me put that down. So I know there's a factor, and I said it would be x plus 1, right? Now, how do I get the other factors? Well, I'm going to put this down for you. And that's going to be x4 minus 46 x squared. And we have many ways of doing this, by the way. I'm not just saying by division. I'm just saying division is like really the simplest thing you could possibly think of. Right? Probably the most intuitive, too. So I know this is going to go in a nice number of times with a remainder of 0. So that'll be x cubed, right? And what do you get? x4. Let's see. What do you get over there? Plus x cubed, right? Subtract, you get minus x cubed minus 46x squared minus 24x plus 21. Well, that's going to be, let's see, that's x cubed. That's going to be minus x squared now, right? So minus x cubed minus x squared. Well, you get minus 45x squared minus 24x plus 21. So I'm going to say minus 45 x, which is minus 45x squared, minus 45x. I'm going to subtract now. What are you going to get? You're going to get, let's see, 21x now, right? Plus 21, which is going to be what? That's going to be plus 21, right? So what do you get there? 21x plus 21, which is equal to 0. So now and again, I know it looks different than work on the piece of paper up here. So let me just go up here. I got a partial factorization of it. Let me just get my eraser out. I'm going to write this down for you. So x4 minus 46x squared minus 24x plus 21. I've determined that x plus 1 is a factor, and I've determined that x cubed minus x squared minus 45x plus 21 is also a factor. All right, I'm going to get my eraser out because I'm sort of like running out of room, and I'm going to just, that's done. I'm going to try to factor the cubic now, and as I move along it's going to get easier. And what I mean by that, cubes are easier than 4-3 polynomials, and then when I get a square, that's even going to be easier. But I'm assuming there's a rational root to this one over here as well. And someone says, I wonder what that could be, and that might be more difficult, but it's at least a lower degree polynomial. So I'm going to be looking at this over here, f of x, whoops, sorry about that. And what's that going to be? X cubed minus x squared minus 45x plus 21. And I know it's exhausting, by the way. So I'm going to put down, possible factors over here. Well, the factors of 21 are 1. It's really the same thing we did before, right? 3, 7, and 21. Well, let's give it a try. And as I go along, I'll just put these down pretty quickly. I like to start with 1. That seems very unproductive. That's not going to work. I'll cross it off. It doesn't give me 0. I'm going to cross that off. Now, I don't think I want to try minus 1, but I'll put it down for you just in case you wonder why I don't want to try it. It's unlikely. That's not working. Don't be frustrated, though. I'm crossing this off the list. Let's try 3. It's more difficult, though. There's no doubt about it. That's why I tried second. 27 minus 9. This looks really unlikely. Minus 135 plus 21. There's no way that's 0. Not even going to add it together. This might be depressing to you, but you keep trying. I'm going to try f. By the way, it's plus or minus. F of minus 3. What do you have there? Minus 27. Minus 9. Plus 135. Plus 21. Now, a lot of students are really good. They can do this in head, and they say, these aren't working. They're not 0. I'm going to cross it off. Now, I realize what students are saying. I don't want to go to 7. By the way, I don't either. But I'm kind of searching through the list, because if it doesn't work out, I got to go back to those other methods about cubics, how to factor a cubic. And I don't think I want to go back to those methods. That's a really tough thing to do. We've done them in the past, remember? Making substitutions. I don't want to go there. Let's try to 7. I know it's tough. And let me write this down. F of 7. Well, 7 cubed, that's 49 times 7. Well, 7 times 50 is 350. Minus 7, 343. Minus 49. Right, that's 7 squared. Now, I'm going to get my ratio. My chicken scratch doesn't look good, but I'll write this down. I got to do 45 times 7, right? That's 280 and 35. That's going to be 315 plus 21. I'm sorry, minus 315. Sorry about that. Minus 315 plus 21. Well, I'm going to take the positive and add them together, and it's going to be 364. I'm going to add the two negative numbers together. That's 315 and 49. Let's see, 9 and 5 is 14, right? 364. Bingo, I found one. So I'm going to say I found another factor, and I'm going to erase all that chicken scratch now. And maybe I shouldn't erase too much chicken scratch. I'll erase this over here. So what do I know now? I know this. I know x plus 1, x minus 7. Now, x minus 7, I'm saying, is a factor of this guy over here, and I got to figure that out now. So I'm going to erase this other chicken scratch over here. I think I did okay. And I'm going to do another long division. I know it's tough. X minus 7 divides into that cubic, and it's getting easier. So after I do this, I'll get a quadratic, and quadratics are really easy to deal with. X squared, it's going to work out nicely, by the way. X cubed minus 7x squared. This will give you 6x squared minus 45x plus 21. This will be plus 6x. That'll give you 6x squared minus 42x. That will give you minus 3x plus 21. I'm going to say minus 3 now. Minus 3x plus 21 is 0. It worked out pretty nicely. So I'll put this over here. So x squared plus 6x minus 3. Now, by the way, once I get it down to the quadratic level, I'm going to erase my long division now. Once I get down to the quadratic level, things should become much easier for me, all right? So what do you mean by much easier? I'm looking at that remaining quadratic, which is x squared plus 6x minus 3, and I'm wondering, when does that equal 0? I'm going to use complete the square. This would equal 3. Half of 6 is 3. Add 9 to both sides. And you're going to get x plus 3, quantity squared. 3 plus 9 is 12. Square root rule, x plus 3 equals plus or minus the root of 12. X would equal minus 3 plus or minus. The square root of 12 is 4 times 3, so it'll be 2 root 3's. So I found 2 additional roots. Right, so what are the roots we found? We found x equals, and I want to remind you what we found. We found minus 1. We found x to be 7. We did that from natural root theorem. And then we're getting these 2 irrational roots, and the 2 rational roots are going to be, let me just call these x1, x2. x3 would be minus 3 plus 2 root 3's, and the other one's going to be x4, it's the 4th root, by the way, minus 3 minus 2 root 3's. These are listed. I want to tell you where they're listed. Let's see, I got this one here. I've got this one here. And let's see if I put these down for you. I got this one, and I got this one. I'm also putting the approximate values down for you. I also have the factored form down for you, and I also have a graph down for you. All right, let's look at the graph. That's the graph over here. And it's not bad. I did the graph. All right, now someone's going to say, did you do the Euler? No, I didn't. But if you want to look at Euler's method, you look over this. All right, you read that. It's not easy, but if I were a machine, it's not bad. Machines do really nice jobs with this stuff over here. But I'm not a machine. I'm looking for something simpler to do. All right? But again, if you want to go into coding, you would need to know there's all kinds of techniques for finding solutions to quadratics and 4th degree polynomials, 3rd degree polynomials. And you look at those techniques that are being covered. They're important techniques. Although no longer covered in algebra, they're important techniques. So let's take a look. And they gave you a graph, by the way, with all 4 roots listed over here. Someone says, why did you approximate them? So I could look at my graph and determine these numbers okay. For example, I said one of them is approximately minus 6.46. That's right over here. Minus 1, that's easy to identify right there. The other one I said was going to be about 0.46. 0.46 is right about here. And the other one was 7, if you recall, and that's right over there. So bingo, we got them. All right, we got a nice little picture over there, sign analysis. What's the exercise about? Let's take a look. Again, what am I doing? I'm actually using rational root theorem. I'm not doing what Euler's method. And again, reason for that is I'm looking for something simple to do. I really am. And I find simple things by using the rational root theorem. And I did it, and I did the graph of it. I got all the roots of it, and I was able to do that using the rational root theorem. All right, there's only one question over there. But I also go through Euler's method. Now, why would I do that? Well, because that's what the section's about. So I don't want to just blow them off and say, I'm not going to do what you're doing because I think there's something easier to do. What do? I also use Euler's method, and I go through it. All right? Now, someone's going to say, I can't remember Euler's method. You're right. Many people can't. So what do? They have it written down somewhere. Where's it written down? It's in the notes, by the way. All right? So let me point out what I mean by that. We're writing stuff down for you. All right? We're writing everything down for you. Is it tough to follow? Yeah, it's tough to follow. All right? Are we recommending you follow it? Yeah. What are we recommending? You start to recognize this. You start to make the substitutions. You plug in the stuff in. Is it easy? No. But I'll be honest with you. For a lot of students, the rational root theorem is not easy either. And why is that? It requires a lot of arithmetic. All right? This one also requires a lot of algebra. Expanding things, collecting terms, yada, yada, yada. But here's what I do. Let me point out what I'm doing over here. So for number one, I actually use Euler's method. I write down what the A is. I write down the B. I write down the C. I write down this equation over here by plugging things in. I simplify it. It's a related cubic equation. By inspection, I get a root to it. What do? I do some long divisions. You get the idea. I'm following that method that was described in this section over here. It's not easy, by the way. What would I prefer to do? I actually prefer to do that rational root theorem. I prefer it, because the other one's just too much work for me. Don't let that create a bias in your own opinion. You might say, no, I want to do this instead. You do what you want. What I do over here, I still did rational root theorem. All right? But I also did the Euler's method. And you want to look through that. It's tough, though. I know it's tough. It's a lot of work for me, too. All right? I went through it as well. Are we getting the same answers? Of course we're getting the same answers. All right? I also talk about how nest roots as well to make them a little bit more presentable. This one over here, rational root theorem. See, it's like my theme, right? But I also present Euler's method for you. You may want to study that. Not to memorize it, but to study it. I wouldn't want to memorize that either, by the way. This one over here, again, rational root theorem. I like it. I try it. I did it. But again, what do I present for you? Euler's method again for the biquadratics. Rational root theorem. But I still do the Euler method. It's a lot of work. Rational root theorem. I did it. I like it. But I also do Euler's method. At least I think I did. Whoops, no. Wait, maybe I did. It's over here. I'm sorry. All right. Man, that's a lot of work. Machines are good at this, though. Be aware of that. Be aware machines are good at it. What kind of machine are we talking about? Well, the people that have made this wonderful open source software, Sage, there's certainly a lot of great mathematicians working on that. They're coders, all right? And if you want to, again, computer algebra system, we've been talking about this for a long time. It's open source. Go to that website, either download it, interactive web-based application, and play around with it. Here's my goal, though. My goal is to get people to look at my work. And why is that? We need to improve it. The best way to improve people's work is to have other people look at it and comment on it. Now, granted, you might not be at the level where you can comment on someone else's work, but what you're doing over here is you're basically looking at the work that we present to you, the answers, and if you think there's an error, you report it to me. So, for example, let's say you're working on problem number, I don't know, let's just go backwards a little bit. It's a really long section, huh? So let's say you made it to the exercises, and you worked on problem number 1, and you didn't agree with what I was doing. You said there's an error. Well, what you do is you email me at that address, that's B as in boy, the @ symbol, NNON, and let me know that you're in exercise 137, you're working problem number 1, and this is why you got it wrong. And I don't mind hearing that from people. I enjoy hearing that from people. Well, what I do, I would carefully look at my work, and I would try to understand what you're talking about, all right? Now, some people said they see errors when there's no errors, but listen, I still appreciate it. But if you do find an error and I agree with it, I will correct the error and I'll give you credit. You'll get credit. You'll be in the book. Your name will be in the book, all right? Unless you tell me not to put your name in the book. But anyway, please, if you need to reach out to me, you know my email address, please do so, all right? Please reach out. Don't hesitate for a moment to reach out. Now, sometimes I fall behind and I lose people's emails because it just gets overwhelming. And if you think I'm ignoring you, email me again and again and again and again, all right? But I'm pretty good with the email stuff, all right? So please consider reaching out to me. Thanks for listening.